And the next speaker is Johannes Kleiner, who's coming from University of Bamberg, and is a brave mathematician that has decided to spend his career doing mathematics of consciousness.
That's right, yeah. Thank you very much, Sonja. Thanks to all of you. It's a very esteemed audience. I'm slightly nervous. A huge thank you to the Breakthrough Prize Foundation. It's a great pleasure to be here. I've learned a lot already, and I'm very grateful to be able to communicate these ideas. Now, in the talk that Ronnie just gave, she, I think, argued very convincingly that consciousness is not only a promising topic, but also a promising young field of research. And I think it has ample avenues for societal applications, and it might arguably change our world and our daily life, for example, regarding pain as one of the key problems of our society. What I want to do in this talk, though, is take you a step further. I want to introduce you to something that's even younger. And that something is called mathematical consciousness science. Roughly speaking, mathematical consciousness science is to consciousness science what mathematical physics is to physics. Mathematical psychology is to psychology. Mathematical neuroscience is to neuroscience. If we had to define it, here's the first definition. Mathematical consciousness science is roughly the application and study of formal and mathematical methods as applied in or relevant to the study of consciousness. And I want to tell you about this because first, it's an emergent field. It has roots already further back in the day, for example, in Roger Penrose's work, which we'll learn about later. But as of late, we really see an explosion of interest. We now have 250 researchers who joined the Learned Society, that is called Association for Mathematical Consciousness Science. We have lots of emergent activities throughout the globe. For example, a large conference series that was actually born right here in Oxford, just up the road in the mathematics department. And most notably, we have a host of open problems and issues. And this talk is not so much intended to be a dissemination of results, but more an invitation to all of you to provide your input if you just happen to be interested, or perhaps if there's a problem that's close to your area of expertise. So what I want to do in this talk then is to exemplify this new area of research by research that matters to this session and this conference, and that is research on synthetic phenomenology. Synthetic means artificial, not naturally evolved. It's created and produced. And phenomenology really just means what Ronnie just told you in this context. It means conscious experiences, what it is likeness, if you've heard that term, phenomenal character. So synthetic phenomenology is experience that is created or produced, experience that did not naturally evolve or occur. And this is the prime example of our day and age. Major contenders for synthetic phenomenology are artificial intelligence, artificial general intelligence, and large language models. And of course, these are the beginnings of the quest of understanding the life as we don't yet know it, or perhaps the life that we're just getting to know. And the first research project that I'll introduce you to in a second concerns the question of whether these systems, the three listed here, can actually be conscious. Now, before I tell you more about this, I should say that I'll introduce you to research, but due to the brevity of time, I will skim over the formalism. I'll show it here and there a little bit just to give some people a feeling, mainly a feeling of how simple it is, but I won't introduce it in detail. Otherwise, we'd sit here for an hour at the very least, mathematicians. Okay, so when you think about these systems that I just had on the other slide, AI, maybe AGI once we have it, one crucial fact is that these are systems that run on these sorts of things, on GPUs or TPUs or DPUs or CPUs. And one thing we can do in mathematical consciousness science is we can look at the designs of the details of these systems. These are high-tech systems in the best sense of the word, and they have tons of properties. And we can see whether these properties are related to synthetic phenomenology. And one property that I'll discuss now is that these systems are verified. They're verified to adhere closely to a formal system in the sense of mathematics. So when you buy a CPU as a company, you don't only get the hardware, but you get information. And one big piece of information is which instruction set architecture that CPU runs. That's basically a set of rules that tell you which computations precisely you can make that CPU do. And these are the computations that end up then being your artificial intelligence or your artificial general intelligence. So what we can do in mathematical consciousness science is we can actually just express the requirements of this verification formally. And that looks something like this. Simple equations. As I said, I will just skip the formalism. The first one talks about functional verification. The second one, post-silicon verification, if anyone heard about these. And we can express these formally and then just play with them. So let's put them in a box for now. It's going to be an assumption we need in just a second. And then we can play with other assumptions. For example, here's one from philosophy. We can study a necessary condition for the scientific investigation of consciousness to be possible, or any understanding, even your own understanding for consciousness. So what's the necessary condition? Well, it's that consciousness makes some difference to a system's behavior. So if you think in terms of Ronnie's talk again, imagine you have someone in an fMRI scanner and the person says, I see blue. You want it to be the case that consciousness makes some difference to that statement. In the best of cases, the person would be caused to say, I see blue, by having an experience of a conscious experience of something blue. If that's not the case for at least some reports or some presses of a button, you're not going to be able to understand consciousness. Now, in the same sense as before, what we can do is we can now take this assumption and we can actually explicate it formally. In this case, there's a little bit more work involved because we have to think about what making a difference means in a good way. And when we do this, we come up with this definition, which again is just for your information if you want to read it. The crucial point is we're calling this definition dynamically relevant, and that's the minimum, most possible way of fleshing out this necessary condition. And then again, we can take it in a box. And now we have two assumptions. That's not much. And what we can do now, we can now go about combining these assumptions. Of course, we didn't know in advance that this was possible, but you actually find that the two formalizations that we have on this slide will actually give you a theorem. And the theorem states that if consciousness is dynamically relevant, that's the second box, artificial intelligence that runs on contemporary computer chips, which are verified, that's the first box, cannot be conscious. So you get quite a strong result from something very general. And that's the name of the game in this part of mathematical consciousness science. Here's the QR code if anyone wanted to read up. That's just December last year in Neuroscience of Consciousness. And that's the first example I wanted to tell you about how, from the mathematical angle, we contribute to the question about synthetic phenomenology. And what this really is an example of an application of a method from another field, in this case, theoretical physics. We're applying no-go theorems, as known in the foundations of physics, to the case of consciousness. But of course, if we know, well, consciousness can't happen on the sort of chips we have right now, well, where then? I mean, these are the artificial systems we're looking at. So the only two options that are there in terms of computations are the following two classes. First of all, we have analog computations. You might know the Antikythera mechanism as one prime example. That's the first known serious analog computer, was created 70 to 60 BC in ancient Greece. That's one class, analog computations. And we have digital computation. Here's again the picture just on the other slide, which goes from physics and transistors and gates all the way up to programming language and algorithms. And it shows the separation of hardware and software right at the instruction set architecture. So these are the only two classes, and the result we've just seen indicates that digital computation might not be the thing that makes a system conscious. And analog computation is implausible from the start as the thing that makes a system conscious. So what then? Well, that prompts us to search for other types of computation. Perhaps there's something we as a society missed. And in fact, we don't have to search much, because here's Geoffrey Hinton, who got the Nobel Prize this year. And in 2022, in a otherwise very unknown paper in section 7 in 2 paragraphs, he introduces this novel concept called mortal computation. So in contrast to the digital computation, which we just had, where you can separate software from hardware, where you need this very tight control over the processor in terms of the instruction set architecture, mortal computation is computation where we can allow for large and unknown variations in the connectivities and in the nonlinearities of different instances of the hardware. It's computation where the parameter values are only useful for one specific hardware instance and don't generalize. And he calls this type of computation mortal because the computation dies with the hardware. It's intimately wound up with the hardware, and you cannot just copy it somewhere else. And you all know the prime example of mortal computation that he has in mind. That's, of course, the human brain, or actually any biological brain. But the point he's making is that perhaps this type of computation, which sort of abstracts from the human computation in the brain, is something that we can create artificially. And in the paper, he gives a few indications of why this might be beneficial for societal and most notably economic reasons. Scale, money, and these sort of things. So what we can do again, we can think about this very long, and we can actually do the same thing we did before. We can formalize this idea. And formalizing this idea leads us to a definition, which for reasons of time I'll just skip because I'd have to say more, but here's just a brief sort of peek into the paper if you want. That's a formulation which literally formalizes what he says. And then we can study the implications of this. And most notably can study this in the context of a theoretical approach to consciousness that's called computational functionalism. Computational functionalism is the idea that consciousness is a computation, a specific computation. When you're in pain, that's because your brain right now runs a specific computation. That's not a general truth, that's an assumption which is widely shared throughout contemporary theories and researchers. And it turns out that if we combine computational functionalism with this definition and make one other assumption, that we can actually prove another theorem. And this time we can show that if this other assumption is true, which I'll just mention in a second, we can actually show this computational functionalism implies that consciousness is a mortal computation, which is kind of shocking because contemporary AI is an immortal computation. So what's the assumption that we need? The assumption is that what's written, I can't point unfortunately, so what's written right above, or can I point? I can point. So the assumption is actually what's written here, namely that immortal computations, those are the computations which are not mortal, are a subset of all Turing computations. That's an assumption that is implicit in what Hinton writes, but we don't know whether it's true. It hinges on the further extrapolation of this new idea of computation, which me and colleagues are involved in. So that's the second result I wanted to share. And this result is actually an example of conceptual engineering at the boundary of adjacent fields. And that's one thing I love about consciousness science and mathematical consciousness sciences. Consciousness is such a striking phenomenon that we have to take the notions around us and rethink them. For example, computation in this case. And the final example I wanted to mention is an example that's not so much related to whether AI is conscious or not, but how it is conscious, what it is conscious of, or in terms of this famous locution, what it is like to be an artificial system. And even there, we have an angle that we can follow into the future. So what we can do, and you probably know this, even so you might not be aware, we can represent consciousness mathematically. Psychophysics has done so for a long time. We can basically create spaces of color experience, that's the first example. We can create spaces of odor, that's the second example. And we can do a number of things. We represent conscious experiences in terms of mathematical structure. But what we're doing now in mathematical consciousness science is taking this a step further, going away from the stimulus cases that we see here and really thinking about how we can represent phenomenology itself, the experience itself, mathematically. And that works. And what it allows us to do is to engage in phenomenology, now with a big P, in mathematical terms. So phenomenology is this subfield of existential philosophy, mostly, introduced by Sartre and Merleau-Ponty and Husserl. And we can now do the same sort of thing in mathematical terms. And we can start to describe the actual lived experience in mathematical terms. And so the first thing that allows us to do is to do something that's called mathematical phenomenology, where we basically use mathematical tools to represent scientifically phenomenology, which is good for theories of consciousness, but also allows us to get an angle on various other topics. That's a first step. And then in a second step, once we've made some progress in terms of mathematical phenomenology, and there is some progress, we're still on the road early, but there's some good progress already. We can then go about doing something that's called computational phenomenology. And that's also happening now as we speak. Roughly speaking, it's the application of mathematical tools now from computational modeling to account for phenomenology. And what people are doing right now is that they basically take the best models of the brain that we have as humankind, as science, and they're trying to model phenomenology in terms of these computational tools. That presupposes mathematical phenomenology because computational tools are mathematical tools, but it goes way beyond them. And this second part is actually where we can get an angle on artificial phenomenology, what it's like to be an AI. Because if we know that an AI system is conscious for other reasons, we can then start looking whether we find the same computational structure, the so-called computational correlates. So that's the third example I wanted to sketch. It's a method or tool where you can represent conscious experiences in terms of mathematical structure and mathematical spaces, and then use that in theories of consciousness or in this research program of computational phenomenology. And I wasn't unsure how to call this, but I think we could call it mathematical philosophy maybe. It's called mathematical phenomenology, and it's an example of philosophy of science. And in this session, though not in my talk, you'll actually see a fourth one, a fourth important application of mathematical consciousness science, and that's Lenore and Manuel's work. And they are really building a model of that's called conscious Turing machine, And that will further enlighten us on how to think about the artificial systems of the future and their consciousness. Okay, so this is a very small subset of what mathematical consciousness science does. I mentioned 250 people are roughly associated with this field now, and there's a bunch of different topics. We work on theories of consciousness, where I think the major effort is really to support the theory building in the field of consciousness science. We find constraints, we propose new theories and models like Kleiner does. We work on improving theories. In particular, if we have new formal models of the brain, in particular if we are looking at artificial intelligence, which are formal systems. We support clarification, understanding, and selection of theories. On the methodological side, we've discussed this already a little bit. We develop and apply formal tools that allow people in the field to study and represent consciousness. And in particular, a big part is exploring theoretical tools from other sciences and seeing how they can help us make progress in consciousness. There's modeling of experiments. We model and analyze the paradigms that are used and think about these, proof results about these. There's work on revising, improving measures of consciousness and tests for consciousness. There's an important part of the work is really on statistics and statistical tools. And there's even beginnings of a measure theory, like in psychology, for consciousness science. And I skipped this box for reason of time, but we've discussed AI consciousness. So this is my talk, and my main objective in this talk really was to introduce you to this novel development, mathematical consciousness science, and to invite you to contribute if you like, or maybe just connect, be interested, share the thoughts that you have. Specifically, I wanted to stress that this is an emergent subfield of consciousness science. As with all emergent subfields, we're in dire lack of funding. Unlike other subfields, we have lots of real-world consequences if we manage to get us below a certain threshold. I illustrated these results based on synthetic phenomenology. The upshot of what I said on the research side is that current AI systems are very, very likely not to be conscious, and even artificial general intelligence that runs on the contemporary computer chips or that are the contemporary forms of computations are not very likely to be conscious. And at the very last slide, which you just saw a second ago, I just wanted to mention that there's so much more work than what I just showed you by many other people. And personally, I'm really just grateful to be part of this field. It's a wonderful research atmosphere. Everyone is super nice to each other. In mathematical consciousness science, I really appreciate that. And so if you're interested, this is our Learn Society, the Association for Mathematical Consciousness Science. Lenore is our president. And you're cordially invited to join. We have this join button. We have a 2-tier membership system, which you will be informed about when you click on the join button. And yeah, this is just an invitation. So a huge thank you, first of all, to all of you for being here and for listening. And second, again, to Sonia for organizing these amazing sessions. And I hope that I was able to help a little bit with these questions. Thank you very much.